Waves on a String lab assignment. You'll need to have your paper with you so that you can read the directions and have the site opened up on your screen. Open the simulation. Number 2, adjust the parameters to the following settings. Select No End. Click that right there, No End. Adjust dampening to none. Select Oscillate. Set the tension to high. It already is. Set the amplitude to 0.75 centimeters. Set the frequency to 2 Hertz. You can incrementally increase it by clicking the arrow or dragging the button. I like to drag the button to get it close and then use the arrow for final adjustments. There's 2 Hertz. Turn on the rulers, timer, and reference line. Rulers, timer, reference line. You can click and drag these rulers to put them where you want to. You can move the reference line too. Number 1, if the simulation isn't creating a wave, click the play button to create a wave. Mine already is. Number 2, pause the simulation so that 2 complete waves are on the screen. Pause. Do I have 2 complete waves? Not yet. I'm going to use this blue button to step it forward. I don't know, maybe right there. That's 2 complete waves. Number 3, measure the distance between one crest and the following crest and enter it here. Okay, let's do that. We're going to measure the distance from one crest to the next crest. And remember that every measurement includes the known part of the measurement, and the last digit is an estimate. I think it looks like 3.1 centimeters. Each of the tick marks is 1/5 of a centimeter. That's 3.2, 3.4, 3.6, 3.8, and 4 centimeters. I think it looks like 3.1 centimeters. I want you to measure very carefully. Yeah, I'm going with 3.1 centimeters. Make sure you have units. What property of the wave did you just measure? From one crest to the next crest, that measurement is the wavelength. Measure the distance between one trough and the following trough. Okay, move your ruler down from trough to trough. Measure carefully. Looks like 3.1 centimeters. How do the values you entered for 3 and 5 compare, and why do you think this is so? They are the same. Okay, why are they the same? Because corresponding points on a wave are the wavelength. I should say the distance between corresponding points. The distance between corresponding points on a wave are the wavelength. Number 7, while it is paused, measure the distance from the center line to the crest of the wave. Okay, the center line to the crest is Measure very carefully. I think that's like 0.2, 0.4, 0.5. It's about a little less than 0.6 because I'm going to look at the center of the bead. I think it's 0.55, 0.55 centimeters. What property of the wave did you just measure? The distance from the center line to the peak or the crest is the amplitude. That's the amplitude of the wave. Number 9, measure the distance between the center line and the trough of the wave and enter it here. Okay, move your ruler from the center line to the trough. I'm going to get that trough, I guess, about right there. I want to measure the center of the bead. About right there. So that's 0.2, 0.4, 0.5, almost 0.6. Is it 0.55? 0.55 centimeters, I guess. Go to the second page. How do the values you entered for 7 and 9 compare? Why do you think this is so? They are equal because amplitude is the maximum displacement of the wave. Maximum displacement. In other words, the distance from the equilibrium to the crest is the same as the distance from the equilibrium to the trough. Either of those represents the amplitude, the maximum displacement. Okay, next part. Determine the speed of the wave with wavelength and frequency. Measure the wavelength of the wave. With the program paused, you can use the step button to incrementally advance the motion of the wave. We already did that. Convert the wavelength to meters and enter it below. Remember, 100 centimeters equals 1 meter. Also, read the frequency from the simulation and enter it as well. Okay, so we already have it set with a frequency of 2 hertz, and we've measured the wavelength. In the first page, the wavelength was 3.1 centimeters. So it said to convert it to meters. 3.1 centimeters times, no, not times, sorry, divided by 100 centimeters per 1 meter equals 0.031 meters. There. I converted from centimeters to meters, and I'll enter that wavelength here. And now to find the wave speed, remember the speed of the wave equals the frequency times the wavelength. So multiply the wavelength with the frequency to get the speed of the wave. I'll let you do that yourself. Step 2. Repeat the previous step with the different frequencies shown in the table below. For some frequencies, you may only see half of a wave. In this case, measure the distance from the crest to the trough and double it to get the wavelength. Okay, let's do it. We're going to set the frequency to 0.5 hertz. And then play it. You can only see half a wavelength when you pause it, so we're going to have to double that. I'm going to start the wave right on the equilibrium line. There. If you have a hard time getting it close, then use this incremental step button. We cannot see the whole wave on the screen, so we're going to measure half a wavelength and double it. So from the start to where it crosses the equilibrium line is half a wavelength. It's 6.25 centimeters. Convert that to meters and you get 0.0625 meters, but you need to multiply that by 2 to get the whole wavelength. Multiply that by 2 and you'll get 0.125 meters. You better double check my math. I did that one in my head. And then calculate the wave speed. The wave speed is wavelength times frequency. So that's 0.125 meters times 0.5 hertz. And that equals, I'll let you do that on your calculator, fill in the value in your table. Okay, let's increase the frequency now to 1 hertz. Increase to 1 hertz, play it, and then stop it and try to get one whole wave. If you cannot get one whole wave, then, wait, oh, I can do it, I can do it. You know what, I'm going to do it in slow motion. That'll help me a lot. Tink. Nope, I missed it. Okay, and then I'll use the step button. There, that was challenging. I can see one whole wave. So from going up, down, and back up, the wavelength looks like 6.25, 6.25 centimeters. But I need to convert that to meters. 6.25 centimeters equals 0.0625 meters. And then calculate the velocity of the wave. You can do that part on your own using your calculator. I've already showed you how. Okay, you're ready to move on. Change the frequency to 1.5 hertz and then repeat those steps. Change the frequency to 2.5 hertz and repeat the steps. Change the frequency to 3 hertz and repeat the steps. Now answer the questions 3, 4, 5, and 6. Keeping the frequency constant, number 3, keeping the frequency constant, try different values for the amplitude. Based on what you observe, how does the amplitude of the wave affect the speed of the wave? Okay, let's keep it at 1 hertz. And I'm going to decrease the amplitude. I'll play it in normal speed. Okay, there's a very low amplitude. Now I'm going to increase the amplitude, and I want you to observe how the speed of the wave changes. Even though the amplitude changes, the speed of the wave does not change. You can write a little note, increasing or decreasing amplitude does not change the speed of the wave. Number 4. Change the wave generator to pulse. Use the timer to time how long it takes for a wave to travel 5 centimeters. You should start the timer when the generator reaches its highest point and stop it when the top of the wave reaches a point 5 centimeters from where it started. Use the speed equation to calculate the speed of the wave. Show your work for this. Okay, let's change it to pulse. And I want to put my reference line at the top of the pulse. I'm going to move up my amplitude so it's something a little easier to see. And I'm going to do it in slow motion. Okay, help me find the top of this pulse. One more time. 1.2. Did you see that? 1.2 centimeters was the peak. Okay, got it. And now I want to put my ruler here so I can measure 5 centimeters. Should actually be right there. Okay, we're going to use the stopwatch over here. This is kind of tricky. You're going to generate the pulse and start the stopwatch when it's at the peak. So you're going to have to be pretty fast. Make sure you do it in slow motion. Start there. 1, 2, ding. That was 0.74 seconds. 0.74 seconds. I'm going to do another trial. And stop. That time I got 1.56. That's a huge difference. Oh, I know why. I forgot to reset the clock. That was not accurate. Do it again. And there, I got 0.76 again. Reset the clock. Let's try that again. And there, 0.74. Okay. I got 0.74 twice, I got 0.76 once, so I guess I'm pretty close. Now let's calculate the speed of the wave. Speed equals the distance traveled, which is 0.05 meters, divided by the time it took, which was 0.745 seconds. I'm just going to go up a little. That's an average of those 3 times. And then you can use your calculator, do the math. When you divide 0.05 meters by 0.745 seconds, what speed did you get? And make sure you write the correct units. You have meters divided by seconds. So your units are meters per second. Number 5. Was the speed what you expected? Was the speed what you expected? And number 6, experiment. Experiment with the different controls to find ways to change the speed of the waves generated. What method did you find to change the speed of the wave? Remember that wave speed only depends on the medium through which it travels. So the amplitude will not change the wave speed. The pulse width will not change the wave speed. Dampening or tension does change properties of the medium. Let's put it on oscillate and see what happens when we increase damping. That changes properties of the medium. See what happens when we change tension to a low tension. Now that wave moves slowly. Not moves slowly, I should say travels slowly along the medium. Please write your answers for 5 and 6. See you later.